Hello everyone and welcome to the NPTEL course on pharmacognosy and phytochemistry. This week we are dwelling into a set of compounds called as glycosides. If you recollect, glycosides are the compounds wherein you have a sugar moiety, which is a glycone, attached to a genin, that is the aglycone moiety. Together, the addition of sugar makes the molecule more polar, whereas the aglycone is the moiety which is responsible for the pharmacological activity of the compounds. Now, from this session onwards, we will see different examples of glycosides. In terms of their biosynthesis, depending upon the aglycones, they might have a numerous biosynthetic pathways such as polyketide biosynthesis for anthraquinone glycosides. They might have acetyl CoA as a precursor if you have a steroyl glycoside, that is via isopentyl pyrophosphate pathway, or they might even have a shikimic acid pathway if they have a flavonoid glycoside. So then the first set of session we are going to dwell on quinones. Now quinones, if you see structural, they are moieties containing ketone. If this ketone, especially a dione, is attached to a benzene moiety, such compounds are called as benzoquinone. If this ketone is or a dione is attached to a naphthalene moiety, it is called as naphthoquinone. And if it is attached to an anthracene moiety, it is called as anthraquinone. Similarly, you have numerous other compounds belonging to the quinone categories, but we limit ourselves to these examples. In this session, we will dwell deeper into two anthraquinone containing glycosides, and those are senna as well as allose. Now, what is the role of this anthraquinones in your plants? Anthraquinones or quinones moieties are very rich source of they do the redox reactions very clearly, and as a result, if you see in our body, the redox reactions are very much required as a part of your electron transport chain. Now what happens here is quinones act as a lipophilic carrier for this ETC chain, and more specifically you might have come across examples such as ubiquinones. So they are the key components of respiratory systems in plants. They help plant undergo numerous other metabolic pathways by their ability to undergo redox reactions, and they are defensive. In some cases they are toxic as well. Now if you see anthraquinones in nature are more predominantly known for their laxative effect, and here are two examples of quinone we will be studying: senna and aloe. Senna and aloe both are known as anthraquinone containing drugs, and both have a strong purgative effect and are traditionally as well as used in modern medicine for this effect. Now let's study in depth about senna. Senna is actually obtained from dried leaflets. Now leaflets are nothing but compound leaves. So if you take a bigger, this is called as a simple leaf, you will see, but in some cases you might come across plants which have compound leaves. So in this case where you have this compound leaves, each component of this, so this particular component is called as leaflet. So senna is actually a dried leaflet, and it is collected from numerous species of senna. The predominant ones which are there in the market are the Alexandrian and the Indian senna. The Cassia senna or Cassia acutifolia, the leaflets of which are sources of Alexandrian senna. The Cassia angustifolia, which is predominantly grown in South Indian region, is also known as your Tinnevelly senna or Indian senna. They belong to the family Leguminosae. In terms of their occurrence or geographical source, if you see your Cassia acutifolia, which is your Alexandrian senna, it grows predominantly along the African regions of Egypt, along the river Nile, in Sudan. And in terms of your Cassia angustifolia, it is growing in Arabia, Somalia and India. If you see Alexandrian senna, it is mostly taken from the wild sources, whereas Indian senna is mostly obtained from the cultivated varieties, chiefly in the Tinnevelly region. If you see this plant is a tiny shrub which is sown mostly during the summer season, and within 1 to 2 months time this plant is ready to harvest. So this plant is then, the branches are taken, dried and the leaves are threshed. Now once the leaves are threshed, you get the dried leaves. Sometimes they are entire, sometimes they are broken. The entire ones come in market for preparation of senna drugs or extraction of senosites, whereas if you see the crude ones which are broken half, they are mostly used directly for the preparation of galenicals. Apart from that, another part of senna which also contains the actives is the senna pods. So senna pods are also available in market for extracting the anthraquinone glycosides out of them. So what are these anthraquinone glycosides which are present in them? So anthraquinones, as you saw, is basically an anthracene moiety. And in this you will see something like this. So in terms of, let me just put the aromaticity, you can just make it clearly aromatic, and then in terms of numbering you can just put it like 1 2 3 4 5 6 7 8 9 10. Okay, so you have this kind of moiety, and this is called as a anthraquinone moiety. In senna, this anthraquinone dimerizes. So you can see here it's not one but two anthracene moieties, 1 and 2. Two anthracene moieties which kind of dimerize. Now once they dimerize, you get what are called as dianthrones. So this dianthrone derivatives are chiefly the chief components of senna, and they are present approximately somewhere between 1.5 to 3% in the range. Now this anthraquinones contain hydroxy groups chiefly at 1 and 8 position. So often they are called as 1,8 dihydroxy. So this 1,8 dihydroxy anthraquinones are joined to each other, and in case of senna they are glycosides. That means they contain your sugar moiety being attached. This sugar is chiefly glucose. So you can see here the sugar is being attached. Now this anthraquinone moieties might be substituted. As you can see here, there is a carboxylic group. So if there is a carboxylic group here, as well as this R, as you see here, this is also a carboxylic group represented by a COOH. It is called as a rhine anthrone. The reason is, you will see that rhine is like this, COOH. So to this anthraquinone, when I put a COOH, I get my rhine. So rhine dianthrone glycoside is basically your senoside. Now depending upon its configuration, specifically with respect to the hydrogen, if it is trans, it is called as senoside A, and if it is a meso, it is called as senoside B. Similarly, instead of CH2OH, if this R is a CH2OH, so you will have one rhine and the second one. So if you replace this by CH2OH, it is called as aloimodine. So if you see of dianthrones, one is rhine, one is aloimodine. In that case, we call it as heterodianthrone. So if this is a heterodianthrone, we call it as senoside C and senoside D. So this senosides C and D are the ones in a similar manner. C contains this hydrogens in a trans configuration, whereas D contains this configuration in a meso form. So you have senoside A, B, C, D as well as senosides E and F are also being reported. Now apart from that, it might have free anthraquinones which do not have sugars, such as aloimodine, rihine. You might have even some compounds like palmidine. Otherwise, even you have monoanthrone glycosides such as rihine glycoside and aloimodine glycoside and so on. So, and dianthrone as well as anthraquinone monoglycosides are the components which are present in senna. Apart from quinones, you will also find flavonoids, chiefly your camphorol and isoramnitin, chrysopanic acid, saponin, salicylic acid and some traces of volatile oil have also been reported. Apart from that, the leaves of senna are known to have mucilage in their epidermal cells which swell when you soak it in water and can be easily stained with ruthenium red. Now, the differentiating point between your Indian senna and Alexandrian senna is a compound called as tinvalin glycoside. So, if you see this compound here, there are two derivatives. So, if you put your R1, R2 specifically here as an H, and if you put here as a glucose, you get what is called as hydroxymazicin. So 6-hydroxymazicin is present in both Indian as well as Alexandrian senna. But in this case, where you have your tinvalin, so R1 gets your H, R2 here you will have your glucose, and R3 instead of glucose you will have your CH3. This is what you call it as a tinvalin glucoside. It is exclusively present in your Indian senna varieties. Apart from that, if you see in terms of appearance, your Alexandrian senna leaflets are little ovate lanceolate, whereas Indian senna are just like kind of lanceolate. Alexandrian are little grayish and they have little marks on them because those Alexandrian ones are generally packed and pressed as bales. So they have those leaf markings also. So that can also help them differentiate. Apart from that, in the subsequent lectures, we'll be doing leaf constants. So Alexandrian and Indian senna can also be differentiated by their leaf constants. Now, chemical test, you can evaluate the anthraquinone glycoside, chiefly the senosides, by a chemical test called as Bontrager's test. Now, what happens in this Bontrager's test is, first you take the drug, as you can see it's a greenish powder of senna, and you need to hydrolyze it. The reason why we need to hydrolyze it is because we want to remove the sugar. The reactivity, we want the OH free. So in order to break this, hydrolysis has to be done, and this can be done by boiling the drug in presence of dilute hydrochloric as well as sulfuric acid. So any of these two would suffice our need. The point is just to get the sugar removed. Now once the sugar is removed, you will see that the molecule becomes very lipophilic in nature. Okay. So what happens here is this lipophilic molecule can then be extracted in chloroform. So to this hydrolysate, that is the solution containing hydrolyzed product, just add little bit of organic solvent, mostly chloroform is added, but you can add your dichloromethane or any organic solvent which dissolves the cyanidins, that is the aglycone. Now you take this compound or this extract, separate the chloroform layer. Now you can see here the chloroform, because it is denser than water, is gone down. You can see there as a separate layer. Now this chloroform layer, when it acquires yellow color, this yellow color is due to the presence of cyanidins. So a chloroform layer acquiring a yellowish shade is a good indication that the free quinones are coming into your organic extract or organic layer. Take this organic layer and then treat it with your base. Now this alkali can be ammonia, your sodium hydroxide or potassium hydroxide. When you take it with a base, what happens is a salt formation occurs. Generally, you can imagine something like this. this is already broken, so you will have your sodium, potassium or ammonium salt being formed, and as a result its solubility in chloroform decreases and solubility in water increases. This anthraquinone which is now formed, which is free of sugars, despite that it will form a salt, a pink color complex, and will get into the ammoniacal or the alkaline layer. So this alkaline layer, when it changes to a cherry pink coloration, is a confirmation that your drug contains anthraquinone. So this is the most predominant test used to check the anthraquinone glycosides. Now the applications of senna is known as laxative for the reason being it contains this dianthrone glycosides. This dianthrone glycosides have ability to irritate the gastric mucosa. As a result, you will see a increased peristaltic movement. Findings also find that it decreases the absorption of water via aquaporin pathway, and this increased water in your intestines along with the increased peristaltic movement leads to its laxative effect. But it is also said that if you continue taking senna for a longer period of time, it is kind of a habit forming. So once your intestine gets used to it, then you will have to take it continually to get the purgative effect. So this is to be taken with prescription definitely, and more of this is expressed, or the effects of this are seen in the lower or the larger intestinal region. This is also suggested as a stimulant laxative during the pregnancy and lactation. Now we go on to the other drugs, and this is something which you've seen. It's an aloe vera which is there in the image. So from this aloe plant you collect the juice which is obtained. Now this juice is obtained generally by making incisions. So cuts are made on the lower part of the leaf, and this juice, whatever it comes out when the cuts are made, is dried, and from that you get what is called as aloes. So aloes are basically, or aloe is an unorganized drug which is obtained by making incisions on the bases of leaves of different species of aloes. Now there are many species of aloes which are there in commerce. The most one is, or the famous ones are aloe berry, aloe vera, aloe barbadensis, aloe ferox. All of them generally clubbed together and put in the family Liliaceae. So aloe berry is commonly known as Socotrine or Zanzibar aloe because of its region of occurrence. Aloe vera, also called as your aloe barbadensis, grown chiefly in your Barbados, or also referred to as your Curaçao oros, or Aloe officinalis. Aloe ferox is actually a hybrid, or a hybrid of this with other species of aloe such as Aloe africana, Aloe spicata. They are all known as Cape aloes. So how do you prepare aloes? So when you cut the aloe leaves at the bases, if you're preparing aloe mucilage at home, you would have seen this. So when you cut along the region of the outer epidermis, you will see some tiny yellow droplets being formed, and if you hold this leaf upright, it will drain a nice yellow color latex. This yellow color latex is what is used in preparation of aloes. So depending upon the regions, the method of preparation do vary, but chiefly the method involves cutting the aloe at its base, allowing the juice to drain. To facilitate it, what is done is they are generally kept in a kerosene or a metal cans. The reason being is they are spinous. They are xerophytic and they are spinous, so you have to be very careful while handling them, and metal containers prevent that. So you wear gloves, keep it in metal containers and let the juice drain. A V-shaped trough about a meter or long is kept so that all the juice that is drained is collected. Now this can be collected in different things depending upon the geography. Some keep it in metal tins, some keep it in plastic sheets, some keep it even in goat or animal skin. Now once it is collected, this is boiled to get rid of water. Now as it evaporates, the color changes, darkens, and eventually you get what is called as aloe stone. Now this after concentration is allowed to dry, and on drying you get this stiff stony like material being formed. Now this aloe stone is the one which is there in market. So it comes under different names depending upon the plant from which it is prepared. Now what does this contain? The chief components of aloe are again anthraquinone glycosides, but little different here from senna is, first thing is in senna you had dianthrones. Here it is a monoanthrone, that is one anthraquinone moiety, and in senna you saw what are called as O glycosides. The point of linkage was an O. In this case the point of linkage is a C. So aloe is an example of a C glycoside containing drug. So here you have, depending upon the isomerism, barbaloin, that is aloin A, isobarballoin, which is aloin B. Now this is like pale yellow crystalline substances. Sometimes it precipitates while you are concentrating. It is present in that higher amount. Apart from that, other minor compounds which are present are the resinous substances, aloesin, aloemodin, which are generally formed when you boil the drug, that is due to hydrolytic decomposition. The other things what you see is, in case of curacao aloes, you will see barbaloresinotanol, and in some cases it is even combined with cinnamic acid. Now socotrine, you will see no isobarballoin. We saw the structure here, isobarballoin. So this is missing in Zanzibar as well as your socotrine aloes. So Cape aloe contains capaloresinotanol combined with same way para-coumaric acid. In other constituents of this are, if you see aloetic acid, aloezone, choline, chrysophynic acid, chrysamic acid, homoallantoin, saponins, coniferyl alcohol, free acids, and so on. Now another important part of aloes is the clear slimy mucilage which you see in the parenchymatous region. So that's made up of glucose, mannose, and uronic acid derivatives. Now aloes can be evaluated in numerous ways. One thing what you can do is a borax test, which is a very distinctive test given by aloes. So in this case what is taken is your aloe stone, you crush it to fine particles and boil it to dissolve. Even despite boiling, you will see there are some components which are insoluble. So in order to get rid of those components, it is filtered through Kieselguhr, and to that filtrate. Now the filtrate definitely have your aloins and glycosides. So those are all coming in water. So that clear filtrate you will take, and then you will add little bit of borax. Now heated to dissolve, you will find that your aloe, especially the aloins, they will react with borax. Now this reaction gives you anthraноls. Now this anthraноls, if you take this little like 1 ml of this to a test tube containing water, about 10 ml, and just observe it under UV, the longer wavelength, that is 365, you will see a typically greenish color fluorescence. This is given because of aloemodin anthranol. Another way to check aloe, again the anthraquinone part of it, is to treat it with bromine water or bromine solution. The more concentrated the better. Now what happens is, when you put it, the aloemodin and the other anthraquinone derivatives get brominated, especially the aloins which are present in the higher concentration. So this bromine derivatives form a yellowish color product, and this yellow precipitate is observed. Then there are nitric acid as well as nitrous acid tests. In nitric acid, you will see, you take your solution, add just 5 ml of, if you take 1% aloe solution and treat it with nitric acid, you will see a range in coloration, a vivid green for Cape aloes, a deep brownish red in case of curacao, and a pale brownish yellow coloration in case of socotrine aloes. Now instead of your Bontrager's test, here your aloes give what is called as modified Bontrager's test. The reason remains the same. If you recollect your Bontrager's test, the first step was hydrolysis. Hydrolysis, what we used there was an acid, hydrochloric acid or dilute sulfuric acid. So if you use those, you will see that the carbon-carbon bond is very difficult to break, and as a result you will not get your anthraquinone or a free anthranol. So in that case, to get your free anthraquinone or an anthranol, instead of just treating it with dilute acids, we also add a Lewis acid called as ferric chloride. So when you add ferric chloride, it facilitates the bond breaking here, resulting in the formation of, or helping in the formation of, anthraquinone. Now you have your free anthraquinone and the same test can be repeated. So what was the test? You hydrolyze the compound glycoside to an anthraquinone. The anthraquinone gets extracted in your chloroform, and this chloroform layer, when you treat it with an alkali, forms pink color or pink red color complex. So same test, just a little addition of 5% ferric chloride to break the CC linkage is what is called as modified Bontrager's test. Now apart from that, to distinguish between different sets of aloes, you have got what is called as Klung's isobarbiloin test or cupraloin test. So if you remember, isobarbiloin was absent in Socotrine and Zanzibar aloes, majorly present in Curaçao and present in a very trace quantities in Cape aloe. So in order to check that, what you do is you take a dilute solution of aloes and add little drop by drop solution of saturated copper sulfate. Now initially all the solutions will form a yellow color coloration. Now to this you go on adding again saturated sodium chloride solution and add or dilute it with excessive alcohol, 90% alcohol. If you get a crimson or a wine color, and which stays for about 4 to 6 hours, it's Curaçao aloes. If you get a coloration but then eventually within some time it changes back to yellow, there is a chance that it's a Cape aloe. But if there is no color change, the color remains yellow itself, in that case there is a good chance that you are dealing with Socotrine or Zanzibar aloes. Now what are uses of aloes? Like your senna, this also has a purgative effect due to its irritant action on your GI mucosa, as well as decrease absorption or decrease reabsorption of water in your gut. Apart from this, the mucilage which is obtained from leaves has gained a wider importance now. It is used in mostly topical creams, preparations such as cosmetics, numerous cosmetics. You will find aloe vera in your soaps, you will find it in your lotions, shampoos, you will find them in your anti-wrinkle or protective creams, and there is a reason for it. One thing is aloe gel, which is a mucilaginous substance, is very soothing and water retaining, so it moisturizes well, and apart from that it contains an enzyme called as carboxypeptidase. Now carboxypeptidase inactivates your bradykinin and produces a anti-inflammatory. So more fresh the juice is, the better the amount of enzyme is and the better is the activity. So it has a good role to play in healing of burns and wounds, and the mucilage is also used nowadays as a hair conditioning agent. So here are few references and image credits which I've used in the session. You can go through for additional reading, and thank you everyone for patient listening.